Jaap van Ekris, who's a senior consultant in risk management in the software industry, and he has been working on a number of different projects, including the safety assessment of the Boeing 787 landing gear control system and other applications in the aviation industry and other areas. And his talk will be about maintaining sleeping giants using quantitative data to optimize system maintenance. So let's please start with your talk.
Yes. Can you hear me?
Yes, I can hear you. Thank you.
Good. Okay. Yes. Sleeping giants. Yes, it works. I work for a small company and we're specialized in quantitative risk analysis and risk-driven maintenance. And I'm going to try to explain how this works. It's basically a method used, for example, in the airline industry, and we use it also for what we call the sleeping giants. And what are those sleeping giants? Those are the storm surge barriers in the Netherlands. As some people might know, the Netherlands is largely below sea level. So keeping the sea out is vital. And these are the most important storm surge barriers we have. You have the Oosterscheldekering, which is in the south of the Netherlands. The Maaslandkering, which protects the port of Rotterdam. The Hollandse IJsselkering, which also protects a part of Rotterdam. And in the end, we have the oldest one, almost 100 years old, over 100 years old even. The Afsluitdijk, which protects a large part of the Netherlands from flooding. The challenge with these systems is that they're largely asleep. You want to have the water moving in and out as it normally goes until you reach the point you say, okay, now it becomes unsafe. And then you want, for example, a storm surge barrier to move. If you look at the Oosterscheldekering, you have 55 big doors. You want to close them all and keep the sea out. But if you have good weather, you want to open them up and have the salt water flush in and keep the ecology going there, because it's the effects of closing down a part, a sea arm basically, or a river is pretty big. And we've seen that the devastating effects in the Netherlands as well. One of the most challenging one is the Maaslandkering. It's a big one. It's complex. It's got two huge arms and is only used once every 10 years. So the biggest problem of those systems is basically, will it wake up if you need it? You can see here there are very nice pictures. Most people probably aren't capable of reading the headlines, but these are national newspapers, and they basically ask the question, will it work? Because there are always technical difficulties. A system like the Maaslandkering consists of about 30,000 components. So there's always one broken down, right? It's basically the law of large numbers. But how will you make sure that when you need the storm surge barrier, that it will work as expected? And that's one of the big challenges there, because testing it, activating it while you have good weather, like in the picture you see in the newspaper there, is challenging. You close down one of the big water transport routes in the Netherlands, and even the most important one. That's the route between the port of Rotterdam and the sea. They don't like that. You have to put a notice in at least 48 hours in advance, and it typically is planned years ahead. And you have to, it's also a risky and expensive operation because you have to do a lot of work ahead because you have to shut down water traffic, but you also have wear and tear on the system. People who are living in the environment or want to basically have some fun on a Saturday evening or a Saturday night will encounter storm surge barriers, so they're typically annoyed by it, and it could even lead to failure. So keep constantly proving that the system works by closing it is pretty hard, and that's one of the big challenges which is found more often in modern society. We have a lot of systems which are in essence safety systems, the safety nets we have to keep us safe. And nobody, if you're not careful and the system works normally or your environment works normally, you never need that safety net. And the big question is, how do you make sure that the safety net is still there and operational? The key for that is avoiding unplanned availability of that safety function. And what you typically see is that during storm season, which is a Dutch term for basically when a lot of storms hit us, which ranges from typically 1st October till end of March. That's the period where we expect the heavy autumn or winter storms, which drive up the water into the arms of the rivers. That's when the storm surge barriers have to be ready. And outside storm season, they're allowed maintenance. But that also puts a burden because you have to make sure that everything is done before that period, and only your maintenance can be performed outside that period. So you have a shift in when you plan availability and unavailability. Tunnels and bridges and locks are basically, they have the same issue, but their use is more spread out. So you can use it 24/7. But you have the benefit that you can plan, for example, a night where you say, well, we're going to close down a tunnel for maintenance activities. The key for us is to reduce unplanned unavailability and make sure that it ends up in the planned maintenance windows. That's, in essence, for a safety perspective, the biggest challenge there. If you look at it, these are the two standards we helped develop for the Ministry of Infrastructure. And it's still the risk-based maintenance that, for example, the airline industry uses. You have, I'll first describe the circles, and then I'll take a deeper dive into it. You have a failure rate, and you say, well, what's the actual performance that results in a maintenance plan? From there, you're going to conduct the maintenance, you're going to execute the plan, and then you're going to see what happens with the performance of the system. If you see that, for example, things are deviating, then you're going to correct the analysis and then modify the maintenance plan again. If you look at it, it all starts with a quantitative risk analysis. For storm surge barriers, it's even in the Dutch law by now that you have to have a quantitative risk analysis to prove, and that's a process that's repeated every 6 months, that you have to prove every 6 months that your maintenance and your technical state of your installation is sufficient to withstand the coming storm season, or you have withstood the storm season. So that's an essential part of that planning process. During system design, all decisions and the performance are designed based on fault reanalysis and FMEAs. So they start with, for example, if you look at the Oostschelde, which is now almost 50 years old, they started with risk analysis. What could bring down the storm surge barrier. These analyses steered the design choices, but they also contain a lot of critical information for planning. If you look at the maintenance planning, the biggest concern you have is that the sleeping giant has died. The fault tree analysis will tell you when the giant has died. So having that relation there and maintaining that relation and actively guarding it is an essential part of the maintenance process there. So the initial fault tree analysis will tell you how important is a component from a design perspective. What defects have long repair times from a design perspective initially, but you can update that from practical experience. There are some components which have long lead times, for example, to be repaired. And that's not because it's a long repair job, but because you need components which are very rare. For example, if you look at the Maaslandkering, they have what they call the bolscharnier, which is a huge ball where the weight of the storm surge barrier leans on. There's only one factory in the world who can make it, and it'll take about 6 months to make a new one. So if you destroy that one, if you destroy the current one, you have 6 months to repair, because that's the speed of the factory and the transportation you need. And one of the key elements we have that also comes from the fault tree analysis is the question which components degrade or fail unnoticed. If you look at this a system which is asleep all the time, you have some enemies which are unseen. Aging, it could be failed during previous use, but as you don't use it intensely, you will only notice it when you need it next. So for example, if you have a storm surge barrier, if you close it and you open it up again, but in the opening you destroy, for example, a power line, you're only going to find out when you're going to close again. So those kind of errors are dormantly present and are very difficult to detect. Maintenance errors is one of the biggest challenges also, because you have a lot of maintenance going on, especially outside the storm season. And if these people make mistakes, you're not going to find it until you're going to use the system. You have a lot of unnoticed failures, which will only be present when you need the system. So basically, when you want a giant to wake up, he's not going to wake up because something happened in the previous period. The biggest example, and you see the big red button there, is an emergency stop. If you see emergency stop in an installation, the big question is the button still functioning? And there's a lot of logic behind an emergency stop. It's not just a switch, just to check if the button is still alive. And that's the kind of logic you need to prevent all these dormant failures. If you look at the ways to detect dormant failure is normal use. You're going to use it. You're going to do some inspections. You're going to see, well, does the button look okay, or is it burned down to the ground? Or you're going to test it. You're going to use it in a specific test or a series of tests. That brings us to different maintenance strategies. The easiest one, I always say, is run to failure. You're basically going to use the system, and when something breaks down, well, you're going to see if you can replace it, when you're going to replace it. That's the most, it's from a component perspective the cheapest, but from a availability perspective, it's also the most dangerous one. If you look at condition-based maintenance, another strategy, then you say, okay, we're going to look at the component and see if the condition suggests that it will soon fail, then we're going to replace it. For example, if you have an engine, if the engine starts to sound bad, you probably need to replace it. Or if it starts to rust, then you're probably going to replace it. And usage-based maintenance, the biggest example I always give is in the airline industry. Your landing gear and the landing gear wear and tear is primarily determined by the number of starts and consequently, of course, landings of the landing gear. So if you used a landing gear 10,000 times, they're gonna replace it no matter what. Basically because they know that from 10,000 on, the landing gear will go down very rapidly and very uncontrollably. So they're going to replace it preemptively. Condition-based maintenance is a very interesting one because it allows you to inspect the system. And if you look at that, here you see a picture, an actual picture of an inspection of a tunnel installation. You can see it takes a lot of work. You will close down the tunnel. So you have some unavailability of your primary function because people have to work inside an environment which is unsafe for them, so they're going to close it down. So you're going to lose access to the tunnel for 2 or 4 hours. It could be dangerous. Technicians typically will have to inspect, in this case, for example, a ventilator. They really have to go deep down into that ventilator and inspect if there's no wear and tear. So it's physically dangerous. And what you typically see after an inspection, not often, but it does happen, is system failures. People have crawled into a ventilator, crawled out again, hit something with their feet typically, and destroyed the ventilator when you need it. It happens on storm surge barriers as well. And that kind of stuff is very difficult to prevent. There's also a downside to inspections. There's an inspection which happened to me a couple of weeks ago on a lake. There is some equipment down on the bottom of that lake. And the essence was, sorry, mandatory inspection, better luck next year. My kids were quite easily convinced that inspections are bad because they hoped to have a swim in that beautiful lake. If you look at optimizing that condition-based maintenance, the key of that is for us, when we start optimizing that maintenance, is determining for each component what's your failure rate if we have it on a run to failure scenario, and what would happen if we start testing it. And you can easily optimize it by simulating the number of tests and increasing it. And typically what you see after 2 or 3 inspections, you see a curve going down and you see it flattening out. So getting a simulation per component, what the inspection rate will do, will help a lot in optimizing that performance. And the key is to always look at the effects on the what we call the top event, and that's of course a barrier not closing or an airplane not landing, etc. So from there on, you can say, okay, what's the effect of an interval? What you typically see in storm surge barriers, but also in airplanes, there are natural frequencies in an object and its maintenance and its life cycle. For example, an airplane comes in every several hundred flight hours. So bringing it forward to that period is very optimal, because then you have the airplane in the hangar as well. In storm surge barriers, you see that as well. We have all storm surge barriers have a closure at the beginning of the storm season to prove they are okay. But during the storm season, you have typical inspection rounds, and these inspection rounds take 2 weeks. So each 2 weeks, a new inspection round will start. So if you can harmonize towards that frequency, you have a lot of effort optimized there. And what you see also, for example, the Easterschelde storm surge barrier, they also move each door every 2 weeks just to see if nothing happened. Those are inspections and tests which are planned. What you see, and that's subject for research, and one of the most beneficial parts of research, can you inspect a system without even touching it? One of the big examples we have in the Netherlands, that for tunnel ventilation systems, what you typically see is that the electric starter behavior, so you turn on the ventilator to maximum power, that behavior, what the ventilator displays then, is very telling of how it will fail in the next coming 3 months. If it starts to use a lot of energy and a very slow startup, then it's very worth your while to remove the ventilator and replace it with a new one. The big thing here is that it's an easy test. You can do it without closing down the tunnel. And the big benefit is that it has enough predictive power to defer the maintenance to the next maintenance window.
Sorry, could you wrap up in the next minutes? Thank you.
I will. If you look at executing maintenance, of course, people have to do the maintenance, actually do it. The big challenge of that kind of maintenance is keeping the clean records of what actually happened. And one of the biggest challenges for data and data analysis is basically a lot of garbage going into the data. Because people will say a complete component has failed or a complete landing gear has failed while only one pump has failed, for example. That kind of stuff is very hard to detect, very hard to clean up, but will kill any kind of statistics you try to execute on it. Coming back, maintenance has been executed, and every so often you have to have some reflection and say, okay, did the system achieve its envisioned performance? Did we do okay? But the more detailed analysis is much more interesting. Seeing you have an envisioned performance analysis, this is how much components could fail. This is the prediction. How did the real life performance of the system do? For example, Rijkswaterstaat, one of our biggest customers, is a very good housekeeper. So we know that from the statistics the manufacturer provide, typically the systems in the field will behave better. So it's a good maintenance strategy for them. Looking at, for example, another one is did contractors, that Q should be an A, did contractors achieve their agreed repair times? Systems failed down. We estimated initially that, for example, a contractor should take 8 hours to replace that part. Did they achieve that, or did they use 10 or 12 hours? Because that could have an impact when the system is down. That feeding back that information, into the model again, closes the loop and creates a better model. For example, what we typically do is Bayesian updates. So you had an assumption, a failure rate or a repair time. You start updating it towards the more realistic data. And by doing that, you get a new fault tree, a better fault tree, a more realistic one. And then you can start planning your maintenance again. Any questions?